Okay, good evening, everyone. So this session we will be covering from where we stopped in the previous sessions. We will be like taking a recap of the major concepts related to our probability, the continuous distributions, then hypothesis testing and inferential statistics. There are some terms in common which we will be referring like every time. So those things we will just recap. What are those terms? How we can interpret those. So that way we will spend some 30 minutes revising what are we learned in the previous sessions and some things that we missed in between so that we can bridge those gaps. And another 30 minutes we will try to spend on inferential statistics and estimation problems. And maybe another 15 minutes if time permits, we will try to solve some problems of each type. Some 2-3 types are there in estimation. So each type we will solve 1 or 2 problems each. So that is our plan for today. So all set. Shall we start? OK, so this was already covered in previous session. So I will just go through in like a fast mode. If at any point you want me to like explain more in detail, you can just interrupt. So basically, when we discussed discrete distributions, we saw what is called the PMF or probability mass function. So that gives me the probability of an event occurring at a particular point. So this suppose it is x equal to 0. This is x equal to 1. So at a point x equal to 0, I had some value. X equal to 1, I had some value. So I called this as probability mass function. So this is applicable for discrete distributions. So similar thing that is applicable for continuous distribution is what is actually called a PDF or probability distribution function. The issue with following a probability mass function similar kind of thing is for continuous is that suppose you consider an interval and suppose this is your probability distribution. Then at this value, suppose it is 1. You cannot tell like this value is like exact value for the value 1. It is like 1, 1.000. You can have infinite number of zeros and suppose there is a 1 after that. So even for that value also probability of is same. So if we try to determine like probability mass function, we will tell that for in a continuous distribution for each specific value, the probability of that corresponding thing is 0. Like that only we will tell, because we are not able to pinpoint exactly at a particular point what is the value, because there is a delta before that and there is a delta after that, which is like uncountably infinite. Because there are infinite number of points in between that 1, 1.0, 1.001. So that kind of way. So we cannot like pinpoint like this probability is for this value. So things like that we cannot use probability mass function. So we go for what is called a probability distribution function. So that gives for a distribution like this, it defines like 2 values A and B in the x-axis. So we will tell probability distribution for values A less than or equal to X less than or equal to B. So like that, if we define the area in this inside below the curve between A and B, whatever the shaded portion I am showing, that will be my probability that the corresponding continuous distribution values occur between the values A and B. So that I will define as what is called a probability density function. Now, if you see again, like there will be like many values like A, B. If I consider again A plus 0.1 will be another value. So if I want to find the distribution values between A and B, I can get it. Now, if I want between A plus 0.1 and B plus 0.1, again it will be different. So I will have to sample one point here, this point here. So within this second set of points, I will have to again find an area. So that is like I cannot use such a thing over my entire distribution. So I need something more simple, a single thing which I can like use to find values at all points in the distribution. For that purpose, we will use what is called a cumulative distribution function. So what it will do is, suppose I have a distribution like this. So then I will define like, suppose this is a point A and it's suppose it starts like this. First, let my point A be here. Let it be here. Let me consider a point A here, A1. So for cumulative distribution function, I will write that the probability that x is less than or equal to a1. As we told, this one side of the interval we are keeping open, so that will be area till a1. So I will define it as a value, let it be p1. Then similarly for another value a2, my area will be starting from minus infinity to a2. So similarly I can define for a2 the value as p2. So like that, again this is my a. So again for a, let it be p3. That will be my value till this point, starting from minus infinity. So like that, if I go on defining, now suppose let's return to the previous case where we considered. So between a and b, I know this probability, it's a CDF like this for this a, CDF like this for b. So CDF of a gives the area till this point, and PDF of CDF of b gives area till this point. So to get the area between a and b, I just have to subtract from a measure like this, probability of CDF values, probability of b minus probability of a. Now in this case, if I again shift like I told in the previous example, if I want the area between p of a plus 0.1 and b plus 0.1, then again same case, I will be having values corresponding to b plus 0.1. So that I can just subtract from that p of a plus 0.1. So with a single value, I can like characterize my entire distribution. So that is advantage with the cumulative distribution function. So that is applicable for discrete as well as continuous distributions. So that is one concept, basic concept. So coming to continuous distribution, similar to what we saw for discrete, we are having different cases like uniform, exponential, normal. So these and all you can just go through the equations and all. It is actually not much important. We will be mostly concerned with normal distributions, which will be like we will be using throughout in our inferential statistics. In that two things that you can equation and all you need not by heart. This thing you just take into mind that expectation of normal distribution, if it's defined as mu, and variance of normal distribution is defined as sigma square, then the corresponding normal distribution you will represent it as n of mu comma sigma square. So like plot and all, the Shirish explained in last session, so I will not go into detail of that. If you plot like this, it will be something like this. The normal PDF will be something like this. CDF will be something like this. And as you can see for the plot shown here, the mean is 1. So the shape will be, as you know, is a bell curve. And at this value of mu, it will be same as mean, median, and mode. So for a normal distribution, mean, median, mode, all these three will be at the point of mu. That is the mean of the distribution. So that is given a mean of a normal distribution, you can find out the median and mode, because for this distribution, all three are the same. Now, similar to PDF CDF case that we saw earlier, we can like define, since in mu and sigma square we have defined. Suppose I want to find probability of this particular value, this particular thing I want. So I want this area. So like that, for each value of mu and sigma, like I will be having n cases. If I have a computer, actually I can directly find it out. But in the olden days, these computers and all were not so common. So even then we needed to solve problems like this. So what people needed something more easier, similar to what we saw earlier for PDF CDF. So that we can something that can be generalized over all kinds of normal curves. So for that, what came up is what is called a standard score. So that how we will define it. Z equal to x minus mu by sigma. So given any distribution of this form, n of mu and sigma square, you can do this centering with the mu, so that the net mean of the distribution will be 0, and scaling with sigma, so that the variance of the resulting distribution will be 1. So like that, once you do, you need to have only one table corresponding to all the areas till 0, till 1, till 2, like that. You need to have only one table. You can use that to find the probabilities or corresponding to normal distribution for any value of mu and sigma square. So that way, what is defined is called a standard normal distribution. So it will be a random variable with 0 mean, mu is equal to 0. As we saw, x minus mu we are doing, and divided by sigma we are doing. So the resultant distribution will be having a variance of 1. So that is what is called a standard normal distribution. So as I told, standard score we can compute by using z equal to x minus mu by sigma. So any distribution with a mean and variance given, we can convert that to a standard normal distribution and find the probability values corresponding to particular values. We will see some examples so that will be clear. And another thing to note about normal distribution is that what is called this Shirish already explained in last session, 68, 95, 99 rule. That means so considering the middle point mu within 1 sigma of the mean, you will have 68.27% of your data. So assume you are 100 data points in the distribution. Out of that, 68 data points will be lying within 1 sigma. Like that, 2 sigma, 95% of data points will be lying between 2 sigma from the middle, and 99% of your data will be lying within 3 sigma of your middle point, that is mu. So that is something that we may have to use very thing like in deriving insights from the data. And as I told, we need to have something like a table to refer when we are doing it manually. When we are doing it in computer, we can directly use Python. That we will see in maybe next Sunday session. With Python, we can directly find the values. So today we will be doing it manually. So we'll use something that is called a standard normal chart. So the chart will be something like this. So if you see, this might not be visible much, especially if you are seeing on mobile, no issues. You can refer it using PDF. This is a standard thing, so everywhere it will be available. So you just need to get the concept how to read a particular value. So if you see something, this is my x equal to 0. So here in the left side of the table, I have values from minus 3.4 to 0, and the right side of the table, I have values towards this 0 to plus 3.4. So how to interpret this table is, suppose I want to find the probabilities. This whatever is shown in the green color is the probability value. So suppose it shows value of probabilities up to z. So suppose my z is minus 2.55. Then what I have to do is I have to find the labels, row and column labels corresponding to minus 2.55. So first to minus 2.5. I have to find from the row label. So I will get minus 2.5. And the second thing, the second digit 0.05, I have to find from the column label. The intersection of these two I have to take. So that will be that is in this case 0.0054 will be my probability for this particular set. The same way only we do for the right side also. So suppose in this case again z equal to let it be 1.98. Then I have to find 1.9. So my 1.9 row label is here. Then I have to find 0.08 column label. Then I have to find the intersection of those two. So 1.9 and 0.8 will be 0.9761. So that will be my probability that the particular sample is less than this thing. Now there are other use cases of this also. Like just now I told like the case when the value is less. Suppose you want the probability that something is more than this. So as you know, the total area under the curve is 1 only. So from this point, like I told, you got the value from this table, what we consider minus 2.55, right? So minus 2.5, you got some value here. So that is corresponding to this area. Now suppose you want the area corresponding to the rest of this, you just have to subtract that from 1. So 0.005. Similarly, this case, this area we computed that is given by minus 1.98, that we saw 1.98, 0.9761. So the remaining area I can compute as minus 1.9761. So like that, I will tell one more case because those things we will be like using throughout in our next examples. Now suppose I want to find out, I have a set here. Suppose I have to find out, this is minus z and plus z, let's assume. And let's see, we will see two more cases where I want to find the area sum of area of this and this. I have to sum and I want to find the area of this. So what I can do is here I got that this area is 0.0054. So since the normal distribution is fully symmetrical, again this shaded part area will also be 0.0054. So this is like left tail. This is like the right tail of the distribution. So sum of the probabilities in both tails will be sum of these two. That will be something like 0.108. So that will be the sum of probabilities of the left tail and the right tail. Now suppose I want to find out the probability of the area excluding the tails. So between this I want to find. Then as I told earlier, I just have to subtract it from 1 as the total area under the curve is 1. So that way I can find the value under. So these things we will be using like throughout in our examples and all that we will be seeing. So suppose you just tell me how you will approach the following problems. So I have a mean of 20. So that will be my mu. I have a standard deviation 3.33. So that will be my sigma. And I will tell 2-3 examples. Suppose I want to find the probability less than 21.11. So first I have to do is Z equal to x minus mu by sigma, right? So for the first case, my x is 21.11 minus mu is 20 divided by 3.33 is my sigma. So that will give me 1 by 3. So that is what 0.33. So to find this value, I have to find from the table the value corresponding to 0.33. So 0.3 is here. No, I changed it, right? 0.3 is here. 0.33 is here. So 0.6293 is my probability for that particular thing. Now suppose I want to find the probability of it less than 26.66. So again same way, 26.66 minus 20 by 3.33. I'll get like what 2. So again you have to find that to find the probability that value is less than that. You have to find the value corresponding to 2, which is 0.9772. Similarly, as I told earlier, suppose I want between 21.11 and 26.66. Then I got one value here corresponding to 21.11 and I got the value here corresponding to 26.66. So I have to what I have to do is 0.9772. That is area till 26 point. From that I have to subtract the area till 0.21.11, 6293. So subtracting these two, I will get the area like this, whatever is between 21.11 and 26.66. Now similarly, if I want to find the probability more than 26.66, then that is 26.66 is 0.99772. So 1 minus that, 1 minus 0.9772 will give me the probability corresponding to this right tail, which is asked in this question. Now similarly, all these 4 things that we considered are like single tail. Now what will be a double tail look like? That is 2-tailed case look like. So I am giving mean 30, standard deviation 5. If I am asked to find the probability that some value is between x minus 30 greater than 5. So from this itself I can know that this 30 is the mean, 5 is the standard deviation. So I am asked to find out the probability that the value is outside the 1 sigma. So that I can directly know because from this I know that the percent is 68.27. So I can directly subtract that from 100, 68.27. I will get something like 0.3173 something I will get. So from the table also you can do the same thing. So 1 sigma is you can know 0.8413 minus 1 sigma is 0.1587. So 0.8413 minus 0.1587. Again you will get the same value, something similar to this. Minus. Okay. So there what you get is like the area between the 68.27 you will get 0.8 minus 0.15. So you will get this 68.27 equivalent. So same thing you had to subtract from 1. So you will get 0.3173. So that is since we have used greater than here. Had it been less than, that will be 68.27. So I hope that much is clear, right? And one more use case I will tell for example. Suppose now we found out given my set scores, I found out the probability. Now suppose given my probability, I want to find out the set score. So that also I will use the same equation. So I will use the same x minus mu by sigma. So in this example, mu is given as 40, sigma is given as 6, and I am given probability corresponding to 45% area to the left, 14% area to the right, like that. So let's see how you can do that. So there is 45% area to the left. So I have to go to my table. I have to find the value 0.45 in this. 0.45, let's see where it is. So if I see here, 0.45. 0.45 will be coming here between this, right? 0.45. So that at this point, if you see at minus 0.12, till that point the area is minus 0.45, and till minus 0.13 it is 0.4. So 0.45 will be lying between this. So I can assume that it is minus 0.125 something, minus 0.125. So that will be my set score corresponding to probability of 45. So that I will substitute here. So minus 0.125 equal to x minus mu I know 40 divided by 6. So this corresponding x I will have to solve. That will give me answer for this first part. Second part is 14% area to the right. So that also similar way we have to do. We have like find 1 minus 0.14. That is 0.86. So we have to find the probability 0.86 from the table. So 0.86 where it is 0.86 somewhere here, right? So 0.86 we can assume like this 0.8599. So we can assume it to be 0.86, right? So that value is 1.08. So same way I will do 1.08 equal to x minus 40 by 6, not 60 here, 6. So that will give this x value will give me my. So these are the two ways in which I can use the normal table. I can with the set score I can find probability of a particular value, and with the probability I can like find the set score corresponding to a particular probability. So that two use cases we will be using throughout in our estimation as well as hypothesis testing cases. Now we will just see one or two examples. So some use cases for normal distribution like that. So if you just see this, suppose we saw binomial distribution and all. Suppose a die is rolled 180 times. Find the probability that the phase 4 will turn up at least 35 times. So we know that probability of phase 4 turning it in one try is 1 by 6. And if I try with turning exactly 35 times is like NCR we can do, right? NCR 1 by 6 raised to 35 and 5 by 6 raised to that 180 minus 35. Things like that if we can solve based on my binomial distribution that we learned earlier. But the question here is at least 35 times. So for like this I have to find 35 times, 36 times, 37 times till 180 times. So that is like very cumbersome, right? So for things like that, we can make use of the fact that a binomial distribution can be in the limiting case it will be same as a normal distribution. So we have to find the mu and sigma and use our set score to find out the corresponding value that we want. So from the binomial distribution we know that E of x equal to what, NP. So n is given here 180, p is given here 1 by 6. And similarly variance of x for binomial distribution we know that it is NPQ. N is 180 here, p is 1 by 6 here, q is 5 by 6 here. So from that you can find the mu and sigma, and same equation that we saw just now you can find it out. Similarly for questions like annual snowfall or something like that, modeled as a normal random variable with mu 60, standard deviation 80. What is the probability that yes, in this first case you have to find the probability in the right tail, right? Suppose 35 is my half 35. So you have to find the probability corresponding to this point. And now second case, suppose there is a mu corresponding to 60. I want to find the probability that snowfall is at least 80. So 80 or more. So I have to find the probability of the right tail. So again, I can approximate it using a x minus mu by sigma formula. I can find the z-score. I will get this probability corresponding to this area. From 1, I can subtract that to find the answer for this. Similarly, the next question is a manufacturer for light bulbs. He tells that it has a lifetime of 800 hours and standard deviation of 40 hours. Find the probability that bulb burns between something. This is similar to what we saw earlier. Given a distribution, I am giving a value A, I am given a value B. So A is like 778, B is like 834. So I have to find the z-scores corresponding to 778 and 834. So from that, I have to find the CDFs from my normal table, and subtracting that, I can find the probability. So that much we will conclude our recap of our normal distribution. So any doubts till this point? Chats. So now onwards, next slide onwards, we'll be moving to our inferential statistics portions.